Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper trending on X, published on August 4th, 2025, about 3 days ago. This paper demonstrates a really significant 1.68 decibel improvement in PSNR, which is a key metric for reconstruction quality, on a challenging real-world dataset. The paper is titled Low Frequency First, Eliminating Floating Artifacts in 3D Gaussian Splatting, and it tackles a very common and annoying problem in these 3D models. It investigates why these weird floating artifacts appear, especially with noisy data, and proposes a new training method that fixes them by prioritizing low-frequency details first. And as I mentioned, this work is getting some attention online. Here's a post from the user Mr. NiRF, who summarizes the paper's main contributions. They highlight the frequency domain analysis that reveals the cause of the artifacts, and then the introduction of the new EFA-GS method that's based on that insight. It's getting some solid engagement, with over 100 likes already, so people are definitely interested in this solution. The authors also include some key figures in their post to illustrate the improvements. Alright, and this figure really illustrates the core idea perfectly. The top row shows what happens with a standard method called EFA-Splatting. You can see the resulting image is full of those floaty, blurry artifacts we mentioned and gets a lower quality score. The diagram suggests this is because the basic building blocks, the Gaussians, are overshrunk and hard to optimize, but then the bottom row shows the new method. Here, the Gaussians are selectively expanded, and the final result is so much cleaner, with a much higher PSNR of 29.46. And this table really puts some numbers to what we just saw. It compares the performance, measured in PSNR, for both the standard EFA-Splatting and the new EFA-GS method. So if we look at the ship scenes test view, you can see the performance drop when you add noise. For the standard method, the quality drops by 2.21 decibels. But for the new EFA-GS method, that drop is only 0.93. It's a significant improvement in robustness against that initial noisy data. Building on that point about noisy data, this next figure gives a great visual comparison. On the far left, in column A, you have the reference images made from clean starting data. Now, look at column B. When you inject noise, you immediately see those floaty artifacts pop up, especially in the water. Column C shows that from a training view, the problem is less obvious. But then, look at the final column. With the new EFA-GS method applied, the scene is clean again. The artifacts are just gone. Okay, so these graphs show us what's happening under the hood during training. The first two plots show that with noisy data, the red dashed lines, the model struggles, cloning more and splitting fewer Gaussians, but the third graph is the real key. It shows the average size of the Gaussians. With the standard method, those red lines, the Gaussians shrink very fast. In contrast, the new method, the blue lines, keeps them larger, forcing the model to learn that crucial low-frequency information first, which prevents the artifacts. So this is the actual logic that makes it all happen. The low-frequency come-first algorithm. It's surprisingly elegant. For each Gaussian, it looks at its gradient, which is basically a measure of how much it's learning. If the gradient is increasing, the algorithm expands that Gaussian to help it learn those important broad shapes. But if the gradient starts to decrease, it means that Gaussian has done its job, so it gets shrunk and split to refine the smaller details. It's a really dynamic way to manage the learning process. So, moving to the results, this table shows how the new method performs on a custom-built, challenging dataset called the real-world low-quality dataset. And the numbers really speak for themselves. When the new EFA-GS method is applied on top of EFA-Splatting, the PSNR jumps by 1.68 decibels. We see a similar boost when it's applied to the original vanilla 3D-GS. It clearly outperforms its baseline across the board, showing just how effective this new approach really is. In conclusion, the key takeaway here is that by intelligently forcing the model to learn broad, low-frequency information first, these researchers have found a robust way to eliminate those distracting floating artifacts, especially in low-quality situations. That's it for this episode.